In this video, we're going to look at doing problems from some of the Chapter E questions, especially related to units of measurements, and being able to use those for things like unit conversions and some density measurements. As a reminder, while I'll be going through problem examples, you also need to review the concepts from the chapter as well. Things like knowing what the different units of measurements are, making sure you know what your conversions are, knowing things like how reliable measurements are related to the concepts of accuracy and precision, as well as how to do significant figures independently of a problem that does any other steps. I'm not going to be looking at any examples that are just sig figs, but I will use appropriate significant figures in each problem I do here. So to start, there we go. Let's look at this conversion. We're going to practice by converting from 128 centimeters to nanometers. So we start here with 128 centimeters. And note, I'm going to show you the way that I recommend. If you are comfortable with being able to go straight from centimeters to nanometers, that is perfectly okay. But if you are uncomfortable with such a thing, it is okay to always go towards your base unit first. Because I know that the thing I recommended was that you learn your base unit conversion, such as there are 100 centimeters and 1 meter. So it's fine to always go towards that base unit and do this as a two-step process. But as you get more comfortable, it's also fine to do it as a one-step process. I just suggest that you show your work in some way so that if you make a mistake, it helps with giving partial credit. So here, I know I need to convert from centimeters to my base unit meters. The reason this means that I need to put centimeters on bottom, because that'll make sure it cancels my centimeters on top in my original question. That's how I know where to place this. And then one of the conversions you had to memorize is there are 100 centimeters in 1 meter. So this will make our centimeters cancel. That's supposed to be a line through the centimeter. And now we're left with meters. But our question asks for nanometers. So now let's convert from meters, now it's on bottom, to nanometers. And we know that there are 10 to the 9th nanometers in 1 meter. So our meters cancel. We can then put it into our calculator. And when we do so, we'll get 128 divided by 100. And then we can multiply it by 10 to the 9th. Remember that it doesn't actually matter the order that you're doing this in, because multiplication and division are communicative. So you could, if you wanted to, for example, multiply everything on top first, then do each of the divisions on bottom. Or you can do like I did and move left to right, which is how I make sure I don't accidentally skip a step. Remember also that anytime you see a 1, you don't have to worry about putting that in your calculator, since multiplying or dividing by 1 simply gives you the answer back. When we do this, I lost my pen, there we go. We'll get an answer, and I'm going to report that as 1.28 times 10 to the 9th nanometers. Remember, I did this because I should have 3 significant figures, since there were 3 in my original question. Also, if you're trying to remember how to do scientific notation, remember that, so this is the number that my calculator actually put out. I gotta make sure I count all the zeros here. So, let's see, we've got 1, 2, there we go, okay. 9th, so yeah, I'm not used to counting quite this many zeros, because I normally just write it in scientific notation. But here we go, this should be the right number. So when we're doing scientific notation, we want to create a number that's before the exponent that's going to be between 1 and 10. So here, right now it's treated, quit doing that PowerPoint, like there's a decimal here. So I'm going to keep moving this decimal until I get to a number between 1 and 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And each time I move this decimal to the left, I am effectively making the number smaller. So I need to have a larger exponent, which is why when I moved it to the left 9 times, I wrote a 9 here for my 10 power. So this means that 1.28 times 10 to the 9th nanometers is the same as the number you have below. So this would be my answer. If we were moving our decimal to the right, because our number was smaller than 1, then we would need a negative exponent. Since each time we move the decimal to the right, it's like we're making the number bigger than it actually is. We do this because it helps us to compare very large numbers to each other. So we want a standard way of getting to a number between 1 and 10. If we just do something like 128 times 10 to the 7th, and then I need to compare that to 12,444 times 10 to the 4th, it becomes more difficult to simply look at the exponents and make comparisons. That's the reason we're doing this, where we do it to where we just have a number between 1 and 10, rather than moving the decimal to somewhere else. Now that we've got this example, let's look at another conversion example, this time with a unit that appears in both the numerator and the denominator. Our question is that if Usain Bolt can run at 10.6 meters per second, can he outrun a car slowly traveling at 15 miles per hour, with the conversion that 1 mile equals 1.609 kilometers. Now, since it's asking me to compare two numbers, it is easiest to do this if they are both in the same unit. So what I'm going to do is I'm going to convert the speed that my car is traveling at into meters per second so that I can compare the two. You could also convert Usain Bolt's speed into miles per hour. Both will work. So I have 15 miles per hour. And when we have that per there, we're going to put on the denominator here. So if we saw this written another way, we might see like miles per hour, or like when you see meters per second. Make sure that you put that hour in the denominator. If you choose to put the hour in the numerator instead, you're likely not to do your conversions correctly. And this is a common error I see, where students will put both units into the numerator and then not do their conversions correctly. So make sure you know where your units go. Now from here, we need to choose one of these at a time to convert, since we want to get from miles to meters and hours to seconds. It doesn't matter what order you go in, but I'm going to choose to convert my miles first. So we're told in the problem that 1 mile, not miles, 1 mile, is 1.609 kilometers. What we also know is we want it in meters. So for every 1 kilometer, we're going to have 1,000 meters. So my miles cancel and my kilometers cancel. And now my numerator is correct. I now have meters. But now we need to finish the problem because getting meters per hour won't help us make a comparison yet. So now I've got to convert from hours to seconds. So in this case, I'm going to put hours in the numerator, since hours is the denominator in our original part of our problem, because I want to cancel that out. So for every 1 hour, I know that there are 60 minutes. And since I don't want it in minutes, I know that for every 1 minute, I now have 60 seconds. So that means that my hours would cancel and my minutes would cancel, and you'll notice I'm left with meters on top and seconds on bottom. So I'm going to plug all of these into my calculator, and when I do so, I'm going to get that I have a total of the car is traveling at 6.70 meters per second. Note that I wrote 3 significant figures since I had 3 in my problem, and this should be a 6. Let me make sure it looks more like 1. That could be a really badly written 0. So 6.70 meters per second. When you see problems like this, make sure you actually finish the problem. Here, simply saying 6.7 meters per second isn't actually the answer. The answer in this case is yes. He can outrun the car. Note that I would be perfectly fine if you just said yes and circled it. Note that simply providing the answer yes without any work will not receive any credit. You need to actually show your work rather than just simply saying yes or no. Now, that's a second example of using a different type of unit conversion. Let's look at one more, this time with a cubic unit. So here, we start with a pool, and it's going to hold 7.5 times 10 to the 4th liters of water. What I want to know is how many cubic meters it holds. Well, the only conversion I know to get between something like liters into some unit that's got an m that's cubed is that a milliliter is equal to a cubic centimeter. So that's the only one I have memorized, and the only one I've asked you to memorize. So I'm going to start by noting that 1 liter contains 1,000 milliliters. I will then convert that every 1 milliliter is also equal to 1 cubic centimeter. And then we can go from cubic centimeters to cubic meters. Now, reminder, you know that 1 meter contains 100 centimeters. However, you can't just plug in 1 meter and 100 centimeters and just put a 3 at the end and have that be okay. Instead, we're going to cube the entire thing on both sides. So when we do that, cubing 1 doesn't change anything, so we just get 1 meter cubed up here. When you cube 100, though, you're going to get 10 to the 6th. Or you could also write it as a million, but 10 to the 6th is a lot easier rather than trying to write all those zeros. We can now check that our liters do indeed cancel, our milliliters cancel, and our cubic centimeters cancel. We can then plug all this into our calculator, and when we do so, we're going to get that our pool would be able to hold 75 cubic meters. So that's how we'll be able to make a conversion when we have a cubic unit. Similarly, if you end up with a square unit, you just need to square both of the conversion factors. It's not that you need to memorize a separate conversion. It's also important to note that this is just from changing a conversion, such as knowing that 1 meter is 100 centimeters is cubed. If in the conversion you memorized it was already a cubic, then you wouldn't need to make any further adjustments. So we'll try one more example here. Here's a fairly straightforward density example. Note that we will use density throughout the course. You're expected to be able to both calculate a density and to be able to convert between mass and volume back and forth. In the future, we'll be using this to do problems that are more involved, where you will start with a density conversion, but you'll do a lot more to it. But here, we're actually asked to find the density. So we know that density is going to be equal to mass over volume. I also know that I want my density units to be in grams per milliliter. So to make the problem easier, I'm going to go ahead and do this conversion. Note, 1 liter, that it's okay if you were to calculate first and then do the conversion after. That's perfectly all right. So 1 liter is equal to 1,000 milliliters. So we get simply 1,000 milliliters. So then and my grams are already okay because that's the mass I would expect. So I plug this in. I have 231 grams divided by 1,000 milliliters. And this is going to be equal to 0.231 grams per milliliter. In this case, you'll notice I have 3 significant figures because both numbers in my problem had 3 significant figures. On the other hand, let's say that this right here had only said 1.0 liters. If that had been the case, then my answer would have just been 0.23 grams per milliliter because it would have fewer significant figures. It wouldn't matter that, there's my pointer, that this number had 3 as you take the least. Similarly, if we had increased this to 231.00000 grams, we measured this super carefully and we had 7 significant figures. That still wouldn't increase the number of significant figures we have in our answer, since we're still limited by one of our 2 volume measurements, depending on which one you had. So remember, when we're doing multiplication and division, we will use either the most, or we'll use the least significant figures, between the different numbers. Remember that for addition and subtraction, you'll be using the least number of decimal places available to you. And I suggest if you don't remember those, that you make sure to practice doing some significant figure problems, because I realize we didn't have to do addition or subtraction in any of the examples here, but it is something you're expected to be able to do for this.